me start by saying it's a great pleasure to be with you, to share with you, albeit virtually, our latest work on construction of human body shape from images and the creation of virtual fitting rooms. I would like to thank Professor Abdulaziz and Professor Youssef for the invite. I hope next time we'll be able to attend the conference in person in beautiful Morocco. I would like also to mention this is a joint work with my students, Miss Lee and Miss Basu. My talk will follow the following structure. I will start by motivating the work, address the problem at hand and the various approaches taken to address it. I will then talk about the approach we took, the why and how of it, and the specific sought after application. Then I will finally conclude and open the floor for discussion and questions. Now, at the core of our work is 3D virtual human body shape reconstruction. This is a very useful and necessary step in many applications, ranging from recognition, virtual reality, generation of video games, 3D animation, and the creation of 3D virtual fitting room, which is the sought after application in this work. This application is timely and is needed and would go hand in hand with the online clothes shopping, allowing the trying on of garments at home with changing poses before ordering them. This also could be updated as often as necessary to accommodate changes in physique, weight, aging, etc., to see how different garments virtually fit you in the comfort of your own home. One word of caution though, this is augmented virtual reality and not alternative realities. Meaning, I would not expect myself to virtually look as James Bond in an Armani suit. That will not happen. Now, with regard to existing reconstruction method, by and large, there are three broad approaches for 3D shape reconstruction. The most intuitive would be the use of 3D scanner or other devices with optical components. The big advantage would be a high resolution 3D point model for the human body. Of course, the drawback would be pricey and it is hard to operate for the layperson. You don't expect to have a virtual fitting room where you are requiring the user to buy a 3D scanner and operate it. The second method will be using a set of images from calibrated camera, where corresponding points from consecutive image can be identified using feature detectors and reconstructed in 3D space using triangulation. The big advantage is that it is at the low cost of the spectrum, but there is a major challenge, and the major challenge would be to establish point correspondences in the different images, which require many images to be taken of the target from different views for full reconstruction. This usually leads to accumulation of error during the image registration and triangulation processes. Now, the third method would be to generate a statistical model of human shapes belonging to the same class, using training set of body shape example to learn the distribution of the different body shape characteristics. The model could be a linear function of various parameters that control the body shape. The creation of a reliable statistical model requires a large number of representative data set for training, which could be a prohibitive overhead cost. So from the previous slides, the previous slides mandate a 3D reconstruction method that is low cost, using small number of images for shape reconstruction, but also mandates the capability of generating a high resolution point set of the shape in its details. Our method achieved the low cost by using two images, which we call two canonical images, and guarantee high resolution model reconstruction using a high resolution generic model. In other words, we use two images and a generic model and try to morph the generic model to be consistent with these two canonical images. Of course, the how of how we do that is exactly what I'll be talking about. Throughout our work, we use the Caesar dataset for generating the generic model as well as for evaluation. This dataset contains 800 3D human body point model of people aging from 18 to 65. Each human body point set has about 6,500 points and is in a standard posture, which is the standing pose with arms and legs open. We generate the generic model by taking the average of this 800 body of examples, and point on the generic models are evenly distributed over the body surface to faithfully capture the shape of the body. The two canonical images are taken from frontal and side view of the person, either using a smartphone or a cam. So what we want to do is basically, we want to morph the generic model into a personalized one, given the two canonical image of the person, so that the coordinates of the points residing on the generic model, when projected on the canonical image spaces, their location are consistent with their corresponding appearances in the canonical image. Of course, it behooves us to find points with equivalent saliency to do that. So, for example, if we consider the red point at the top of the head on the generic model, and that on the frontal image and side image of the person, we can see that these 3 points are equivalent, i.e. they have the same saliency. This implies that the red point on the generic model, when projected onto the XY plane, which is the frontal image space, should change its X and Y coordinate to be that of the red dot, small x and y in the frontal image. Namely, the red point would now assume the coordinates small x, small y, and big Z as its new coordinates. When the updated point, small x, y, and capital Z is projected onto the YZ plane, now it would change its Y Z coordinate so to be that of the red point, small y and small z on the side image, hence a personalized update from capital X, Y, and Z on the generic to small x, small y, and small z, consistent with the two canonical image. Now, what made that possible was the finding of equivalent saliency between these points. So we need to address the point of what points have equivalent saliency and how to get them. And also, can we go about derive equivalent saliency systematically, going from a small set of what I call anthropometric points to points with less obvious saliency. And this is what I'm going to do next. A point of less obvious saliency could be the blue point on the generic point, and which points is the one that correspond to it, which are the many blue points on the frontal image, for instance. So our solution is to find a small set of anthropometric salient control points on the generic model and go about identifying their equivalent in the frontal and side images. Then, using indexing in a loop subdivision process, we to track down the correspondences in the high resolution projected generic and their corresponding one in the image. So inherent to this approach is the finding of that saliency map for both the generic scatter point model as well as the canonical image of the specific model we want to construct. As I said, our solution is to start with a small set of anthropometric salient control points and find and identify their equivalent on the frontal and side image. The problem is that in general, free-form scatter points lack saliency and topological meaning, which render the finding of correspondences between points on the 3D generic model and the two canonical images quite challenging, to say the least. We choose a small set of salient control points in the projected canonical spaces that reside on the boundary silhouettes. This should be intrinsic to all individual, and then proceed to generate additional ones from them. The control points could be anthropometric points, such as shoulder points, elbow point, etc., but they could also be fiducial points on the boundary with geometric significance. For instance, we can talk about inflection point, corner points, etc. Now, with regard to the generic model, we can find those anthropometric points, which are the control points on the boundary, and we can do it manually, since this is done once and offline. We can also try to do the same thing for the canonical images, but what that implies is that if we devise an application like virtual reality or virtual fitting room, then we were requiring the user to go and find those anthropometric images, anthropometric points on the contour or on the silhouette of the images they've taken, which is a demand far exceeding the applicability of such an app. Hence, we would also like to try to automate that part so that the user doesn't have to do anything other than take a picture of him, a couple of pictures, frontal and side, of himself or herself. So what the way we're doing that, we are going to do that automatically, is use either a convolutional neural network or an active shape model that will train on a set of representative shapes. For the convolutional neural network, it will take images, frontal images and side images, go offline and get their points, the anthropometric points on their boundary, and then train the neural network to identify where the location of these anthropometric points for a new image. So that when the individual takes his or her image frontal and side, he or she inputs that image into the convolutional neural network, and at the output will be, this is where the anthropometric control points will reside on the silhouettes of the frontal and on the side image. This is the structure of the convolutional network that does that. It takes a grayscale input image and output the coordinate of the control point. It has 5 convolutional layers, each followed by a max pooling layer. The convolutional and max pooling layer are followed by 3 fully connected linear layers, the last of which output the coordinate points. 100 sample out of the 800 from the available Caesar dataset are used for training. So when we're going to evaluate our reconstruction, the goodness of our reconstruction, we are not going to use the 100 sample that were used for training, but rather the 700 remaining in the available dataset. Just a footnote. So as shown in this example, you could see where the canonical images, you have two canonical images fed to the CNN, which spit out the control points. As the predicted point might not always lie at the boundary of the silhouette, these points that do not reside migrate to the closest point on the boundary, which then become the predicted control points. So at the end of that process, you give me a frontal image and a side image of the individual, and it goes through that box, that CNN box with the boundary regularization, and it comes back and tells me what are the control points, the anthropometric control points that reside on the boundary of the silhouette in the frontal, for the frontal image and for the side images, which correspond to the ones that were picked for the generic model. So to generate, so what we have done here is basically say we have a way of identifying the small set of anthropometric points on the generic model and their equivalent one on the frontal and the side images. But these are few points. What we need to do is doing it for all the points on the generic model and find their equivalent salient points on the frontal and the side image, so that, as I indicated with the red dots, I can change or I can morph the generic model into the personalized model in accordance with the frontal and the side images of that person. To make that point clear, suppose we start with points, I'm calling them A prime, capital A prime, B prime, C prime, D prime, E prime, and F prime. Suppose they reside on the generic model. So these are 3D points, and they are projected on the frontal space and now appear as point A, B, C, D, and F, where A, B, C are control points on the frontal projection of the generic model. That means in this example, A, capital B, capital C reside on the contour of the silhouette in the frontal of the projected frontal image, whereas point capital D, capital E, capital F are interior points. And we, using the convolutional neural network, for the frontal image of the specific individual, we find out that we have points small a, small b, and small c are equivalent salient point or control points to capital A, capital B, capital C. So what we want to do next is to say, how about the interior point D, E, and F? What are their equivalent from the set, the brown set, E, F, G, H, and D. So what are the 3 points that I can declare are equivalent salient points to D, E, and F, and how do I obtain them? The way we do it is we use loop subdivision, where in the first step we form a triangle from the point capital A, capital B, capital C for the projected generic and frontal generic, and the same thing for the frontal image. Then we take the midpoint of each of the sides of this triangle that gives rise to the point 1, 2, and 3 in the projected generic frontal and in the frontal image of the individual. Then we look if we have we set an epsilon radius around point 1, 2, and 3 and see, is there a point that falls within that epsilon radius in the projected generic frontal and in the frontal image. So for example, if I look at capital D, the point capital D, it will fall within the epsilon radius of 0.1. Similarly, point small f will fall also within the radius of 0.1. Since these 2 points have the same index, then I will declare capital D and capital F as having equivalent saliency. Similarly, I will declare capital F and small d as having the same index, which is 2, and have equivalent saliency. Now, for the last point in that simplified example, I could see that E does not fall within any of the epsilon of 3. So what I need to do is to go and repeat the loop subdivision again by taking one of the 4 small triangles and take the midpoint and repeat the process. And in that case, I've generated an index point, a midpoint 4, for which the point capital E is in its epsilon radius neighborhood, as well as the point H. And in that case, then I would declare point E and point H as equivalent salient points. And of course, in this simplified example, in reality, I will not have just a few points like this. I will have a lot of points, and I will have to repeat the loop subdivision again and again and again. Now, until I establish all this saliency, and also I would do that for the side images. A few observations are in order here. Declaring saliency between the set capital A, B, C, D, E, and F, and a subset of the small a, B, C, D, E, F, and J means also that I have declared saliency between the 3D points on the generic model whose projection on the frontal image is the set capital A, capital B, up till capital F, and the subset of A, B, C, D. Secondly, if I look at those midpoints, these midpoints are intrinsic salient points. And by that I mean they are preserved under the affine transformation, which is basically the transformation that relates images, or the projective transformation. It's not perspective, it's locally affine. So that means that if you subject a line to an affine transformation, the midpoint is going to be preserved, meaning it will appear as a midpoint after the transformation as it did before. So that is an important point to raise. We can see the equivalent saliency established in the dense space. Points on the generic model will have equivalent saliency to the one on the canonical image. And you could see that on you could see the loop subdivision, and you could see how the loop subdivision proceeds as the number of subdivision goes on and on. So once we have equivalent saliency, now we are ready to do what we did with the red dot that I talked about a few slides before, and that is morph the coordinate of these points would have equivalent saliency so that they are consistent with the individual. So what you could see here is on the left-hand side, the 3D generic model, after finding the saliency with the loop subdivision, is morphed into the personalized model that you could see on the right-hand side. So this guy becomes this guy. Now we would like to also evaluate the goodness of our reconstruction methods. And in order to do that, we compute the average error distance between point on the reconstructed individual and the nearest neighbor points on the true base model for the 700 different individuals in the Caesar dataset. and compare that error to the average scanning resolution for that Caesar dataset. And just note, the resolution cell is the average of the length of side of the triangle in a delineate triangulation mesh. The mean length of for resolution cell turns out to be about 17.8 millimeter with a 5.04 standard deviation. So we can declare that our reconstruction method is successful if we end up with error distances that are below resolution, at or below resolution. If it comes back and tells me it's 3 resolution cell, 4 resolution cell, then that is an indicator that the reconstruction is not really that successful. So, so for our reconstruction method, we found that the average geometric error computed over all points and over 700 models was found to be 5.46. Now this 5.46 is about 0.3 of the resolution cell. Just a note, when we have a specific reconstruct for an individual, xi would be a point on the 3D model, and yi would be the nearest neighbor in the reconstructed model to xi. So the bottom line here is that based on 700 individual in the Caesar data set, the reconstruction of each of these individuals led to an average error, which is sub-resolution. So at least it's a good flag of an indicator that we're doing the right thing. Now comes the fun of reconstructing the virtual fitting room. So what we'd like to do, since we're able to, from 2 images and a generic model, are able to reconstruct a 3D model of the person, what we would like to do is to fit that shape with garments so that you can have basically a virtual fitting room. Just a note, we would like to minimize the task requested from the user. So for example, we would ask the user to take a couple of pictures of himself or herself, perhaps a video of fitting articulation, and use a picture of the garment that the user wants to see. Either these are given online or in a catalog or what have you. So we would like the user not to be involved more than that. Take a couple of pictures of yourself, one frontal, one side, just import the image of the garment that you want to fit, and this app is going to do its magic and show you in 3D how you would look like in that garment. What we would not ask the user to do is take body-specific measurement, but let the system or the app assumes the role of a tailor. So this allows for a simple virtual fitting room that the user can use to assess at home or anywhere else whether online ordering of the garment is desirable or not. And again, I should emphasize that what that app would not do is make you look differently than what you are. So you want to really have a good assessment as whether the garment fits you, or are you interested in ordering it online or you're not. Now, with regard to the garments, you can have 2 types. One type would be a tight close, which is slim fit, and the one is a loose. An example of a tight fit would be a shirt, for instance, and a type of a loose clothes will be like a skirt or a dress. For the sake of time, since I've been told that I only have 30 minutes, I will skip how we reconstruct type 2 and concentrate on type 1 and show how we proceed with the virtual fitting room for the type 1, which are tight close fitting. Just remember, what is given is a picture of the garment and its type. So if we're given, for instance, a frontal and back image of the garment, then the first step is to construct a personalized 3D garment to fit the personalized model with the appearance of the garment mapped on the 3D personalized model. But this we have done already, and it will follow the exact procedure for the 3D reconstruction, where this time we need to identify the equivalent control points on the garment corresponding to the personalized model, then morph them on the garment. I think, let me see, am I taking too much time?
We're in the Q&A period, but we can keep going for a little bit to
okay, so can I have 5 more minutes? Is that okay?
Yes.
Brilliant, thank you so much. Then we can use loop subdivision and indexing to find the high resolution point correspondence, as was done in the first part of my talk. Once that is done, we import the appearance of points on the garment to their corresponding one on the 3D. So in other words, what we're doing is we take an image, frontal and back, and construct almost like a fitted 3D garment that will fit on top of the shape of the object, of the person. You could see that as an example, you see the virtual appearance. On the left-hand side, you have the person. The shirt that she's wearing is not the one that she's fitting. The one that she's fitting is the gray t-shirt, the Urban Armor t-shirt, and you could see how it virtually will appear on her from the front and the back. We could also do that for different types, and although I did not talk about how what is the model for loose, but you could see how that person can fit loose as well as fitted garments, and virtually look at them from any angle to assess whether they like the fitting or not. An extension of that work, which I intended to talk about here, but because of time, I will not be able to. I can also have an articulation video where I could look at the garment at different articulations. So the person is not just limited to one pose, but a bunch of them. So this comes to, that brings me to the conclusion. What we have done was constructed equivalent saliency mapped between points on the canonical image and the generic model. Remember, the points on the generic model lack saliency, topological meaning, and relational interconnection, but we are able to give them interconnection and saliency. We exploited a set of anthropometric points residing on the silhouette contour in the canonical images to start jump the creation of that saliency map and use CNN or ASM, which is, it's not ACM, it's ASM, active shape model to automatically find them on the canonical image. We also have made use of indexing in a loop subdivision process to lend equivalent saliency to point on the generic model and the canonical images. And then finally, we were able to morph the coordinates of points on the generic model in accordance with their saliency, equivalency in the canonical image, resulting in the morphing of the generic model into the specific model of the specific individual. And finally, we were able to make use of that in creating a user-friendly virtual 3D fitting room app that helped to visualize garment from 2D image in 3D space virtually. The content of what I presented is appears in a paper in in press, shortly to appear in the Journal of Multimedia Tools and Application. And this is the reference. So I would like to thank you very much for allowing me a few more minutes and for your presence to follow what I've done. And now the floor is all yours.
Thank you very much, Professor Cohen. We have a question that is in the Q&A window. It starts with, I wonder if this technique of 3D construction from two images, the frontal and the side, can help plastic surgery for those who likes a look shape image if they had to reconstruct.
That perhaps this would be another application, although it has to be studied closer. But yes, if I'm able to reconstruct, and if the next step is to be able to say, well, this is how I would morph surgically or virtually, how I would morph the part of the body that need surgical intervention, then I will say yes, it is a possible application, and a very interesting one for that matter. Good.
Let me ask a question. I'll wait for some of the other people to type some Q&A in the
Sure.
chat window there. I know that during this COVID situation, some of us had changed body shapes. Luckily, I've gone in the right direction with going down in weight as opposed to going up. So the question is, in this 3D fitting, are you able to tell measurements? Like I'll pick waist or inseam for my pants. Or is that not looked at yet?
No, that is looked at actually, and we, although I did not show it in this talk, we also compare when we do the evaluation. We're measuring parts, as you were saying, and see measurement how they compare to even different methods, and that is in this paper, in the paper that I alluded to. So yes, indeed, you can translate into with the fit, if you concentrate on parts and do measurement, how do this part, what is the goodness of the fit compared to others? And are you, if you have in the COVID, before COVID, you had those measurements, what are those measurements now, as you indicated? Basically, since the requirement from the user is nothing but taking a frontal and a side image, then they could do that every few months before and after COVID, and see what kind of fitting they are getting in terms of reconstruction for their body, and do this measurements that you're talking about to assess whether they have gained weight or did not.
One other question that I had, let's think back to the skirt fitting.
Sure.
Is this a combination of I'll call it the t-shirt fitting, where the waist is on the fitted side of it and the rest is kind of just draped? Is that how you're?
Correct. Okay. And then you add wrinkle to it as well, that you get to by looking at the shadows in the image.
Okay.
So it's more complicated. So it has definitely anchor points, which is as you have indicated on the waist, and then the rest is the flow. And then with the flow, depending on the image, if there are shadow, that means there are wrinkles in the shirt, and then you have to look at that. I don't know why this is not moving anymore.
We have another question in the Q&A window. Thank you. It was a wonderful presentation. My question is about the regression method that you've used on the typical body. What type of method do you use?
So this is with the neural network?
I'm not sure. This was just what was typed into the window, so I'm reading for you.
Yes, so that's just hold on. Let me. I'm trying to get to that slide. So we use the feed-forward system. The loss function was a mean square error function. The activation function was a reloop, and the optimization function used was Adam optimizer. And the error propagation was a backward error propagation. So these are the what my students used to implement this neural network.
Good, good. Thank you very much. We will stop with the question answered about here on this one. I really enjoyed your talk today, sir.
Thank you so much.